Hi, my name is James McGarriotis, and I'm a mechanical engineering student at Drexel University. And this is my simulink solution for implementation on low-cost hardware. This particular model is for use with an Arduino Do. I mean, it can be used with any Arduino. I've been using it with the Arduino Do and the adafruit BNO-055 IMU for absolute orientation. This particular simulink model is meant to serve as a development environment for my 3D printed inverted pendulum robot. This robot was printed on a flash forged 3D printer, and all the electronics were purchased and assembled myself. I've been using this model in order to debug outputs and design controllers. This block here serves as the driver for the BNO-055 IMU. As you can see here, basically it's just a simple implementation of Arduino I2C communication blocks. The values I'm interested in here are gyroscope angular velocity values and also quaternions. The quaternions are then converted to Euler angles using a built-in conversion block from Simulink. This block here outputs the counts of each of the geared motors' quadrature encoders. These counts are then passed to a subsystem which converts these counts into a measure of angles using 480 counts per revolution of the geared shaft. Angular velocities can also be calculated as a simple derivative. These values are then passed to a converter which converts rotational values into linear values. This conversion, using the wheel radius, just averages the two values to get a single linear position and velocity value for the entire inverted pendulum robot. Last but not least, we have the motor driver block. The motor driver block basically accepts two voltage inputs. My DC motors are 12 volts, so these inputs can range from 12 to negative 12 volts. Each motor has its own separate driver, and as you can see, they're basically converted to duty cycles, and one digital pin controls direction, the other is a pulse width modulation that the input is converted from 0 to 255 for an 8-bit value, and output with a simple PWM Arduino block. In order to keep it simple here, I've only implemented just a simple proportional gain controller in order to demonstrate how the motors can respond to changes in the pendulum's angle. Now here I'm going to demonstrate what happens as I tilt the inverted pendulum robot. You can observe the outputs and see how the various motor speeds and angles recorded by the IMU unit change here. I will now demonstrate a simple model built to the inverted pendulum robot, deployed as a standalone module. For simplicity's sake, I've only used the IMU and motor driver block and implemented a simple PD controller that will attempt to keep the pitch angle of the inverted pendulum robot at 0. This should, in theory, keep the inverted pendulum robot vertical. I've left out the quadrature encoder blocks in order to keep it simple for demonstration purposes. Now, as you can see, the robot is able to maintain upright stability due to this simple PD controller. It seems that this standalone model works very well with the Simulink solution. I've been exploring different controller designs for future implementation. As you can see here, I've also developed a series of output blocks that can be used with the IMU block. In my previous simulation, I only used quaternion and gyroscope data, but magnetometer, accelerometer, and Euler angles are able to be extracted directly from the IMU. In this video, I have demonstrated how Simulink can be used for controller design for deployment on low-cost hardware such as the Arduino. As all of you probably know, taking controller design from theory to practice can be much more difficult than expected. Simulink seems to serve as an easy way to mitigate some of those problems, in that you can design your controller right here on Simulink and deploy your solution directly to your Arduino with very little difficulty. Through the use of the blocks that I have designed and outlined in this video here, Arduino controller design can be made incredibly easy. Using the IMU block, absolute orientation values are very easily output and analyzed using Simulink. The cart position can be easily tracked, or any motor for that matter can be easily tracked using my quadrature encoder S function. The motor driver allows for a controller output to be easily sent to your motor, making any Arduino project essentially just a matter of designing your own controller. These three blocks make all of your output observable, which can make implementing a controller on open source hardware such as the Arduino a very simple task. Thank you for watching my submission to the MATLAB Simulink Hardware Challenge. My name is James Megariotis, and I'm a mechanical engineering student at Drexel University. I hope you all use my solution in the future, and here at the end I've provided a few pictures of my inverted pendulum robot for you to see. The entire body is 3D printed. I hope you've enjoyed this presentation. Thank you.